June 3, 1985. A woman arrives at the Regional Oncology Center in Kenstown, Georgia, for her scheduled cancer treatment. She is set for a routine radiation therapy session, safe, precise, a well-refined technology. The machine she is about to use is the Therac-25, an ultra-modern device, the pride of AECL, a leap forward for medicine. The patient lies down on the table. The operator starts the program, and within seconds, the woman jerks off the table in pain, screaming that she's been severely burned. The technician insists that's impossible. But this was only the beginning. The story of the Therac-25 would become one of the deadliest catastrophes in the history of medical equipment. Therac-25 was introduced in 1982 by the Canadian company AECL, part of their nuclear technology division. It was the third machine in a line of radiation therapy devices, following the Therac-6 and Therac-20. Its number represented the maximum energy in mega-electron volts, with higher energy enabling deeper, more effective treatment of tumors. Unlike its predecessors, which required manual operation, the Therac-25 was fully computer-controlled, promising faster treatment with fewer human errors. Doctors and engineers hailed it as a breakthrough in oncology. Radiation therapy itself isn't new. Since the 1950s, it has been used to destroy cancer cells by damaging their DNA. By the 1970s, CT scanning allowed doctors to target tumors more precisely, minimizing harm to healthy tissue. But while the technology was powerful, it was also unforgiving. Too much radiation could kill. On June 3, 1985, Kathy Yarborough, 61, underwent treatment at Kenstown. She was receiving a standard dose of 10 MeV radiation to the area where her breast tumor had been removed. Almost immediately, Kathy felt an intense burning sensation. The operator examined her, found no visible injuries, and sent her home. Over the next few days, her skin became red and painfully swollen. Eventually, an open radiation burn developed, and doctors calculated that Kathy had received 15,000 to 20,000 rads, far above the therapeutic dose of 200 rads, and even above the lethal dose of 1,000 rads. Kathy lost her breath to save her life and endured constant pain and nerve damage in her arm. She later sued AECL, which settled out of court. Tragically, she died in a car accident in 1990. Within months, similar incidents occurred in Canada and the United States, some of them fatal, highlighting a pattern that nobody initially understood. Less than 2 months later, a 40-year-old woman in Hamilton, Ontario, received treatment for cervical cancer. Within seconds, the machine displayed no dose, yet radiation continued. She suffered 17,000 rads, damaging tissue so severely that part of her hip had to be replaced. AECL engineers traced the problem to microswitch failure and flawed software design. Modifications were made, an extra safety switch, and updated software checks, but the tragedies were not over. In December 1985, a woman in Yakima, Washington, suffered radiation burns requiring multiple skin grafts. She survived. On March 21, 1986, Ray Cox in Tyler, Texas, experienced severe burns, paralysis, and organ damage, dying 5 months later. In April, another patient, 66-year-old Vernon Keith, died from brain radiation overdose. It became clear something was deeply wrong with Therac-25.
Investigations revealed a critical flaw in the machine's software, never present in older models. The Therac-25 relied entirely on programmed safety checks, replacing the physical interlocks used in earlier machines. The software was written by a single programmer on a PDP-11 in assembly language. While the hardware was tested extensively, the code was not independently reviewed. The most dangerous bug, later called Error 54, occurred when the operator switched modes, for example from X-ray to electron mode and back. In rare cases, the rotating beam table moved incorrectly, delivering a massive overdose of radiation. To make matters worse, the machine frequently displayed cryptic numeric error messages, such as Error 1, Error 2, or Error 54, without explanation. Operators accustomed to minor glitches often ignored them, but Error 54 could kill. Another software issue involved an overflow in the error counter. The machine counted errors in a single byte, 0 to 255. When it exceeded 255, the counter reset to 0, allowing the machine to continue operating even with unresolved errors, leading to further overdoses. Patients like Ray Cox and Vernon Keith, treated in Texas in 1986, received doses between 17,000 and 25,000 rads. They suffered burns, paralysis, organ damage, and eventually death. It wasn't until physicist Mr. Fritz Heiger conducted detailed tests that the underlying software bugs were identified. Only then did regulators at the FDA step in, ordering all Therac-25 machines temporarily removed from service. AECL deployed software fixes and resumed treatment in 1986, but another fatal accident occurred in 1987 due to the error counter overflow. By then, hospitals began withdrawing the machines entirely.
Here's the heart of the disaster: the software itself. The key variable, MEOS. Therac-25 stored beam mode, energy, and table position in a single 2-byte variable. High byte, beam type, electron, X-ray, plus energy. Low byte, table position. All commands for both mechanical movement and radiation delivery referenced this one variable. Two subprograms accessed it simultaneously. Hand controlled the mechanical table and magnets, and data end processed operator inputs. There were no locks or synchronization between them. If they ran at the same time, MEOS could be partially updated. The 6-second death window. If an operator quickly switched modes, X-ray to electron, hand was still moving magnets for the old mode. Data ant updated the variable prematurely. During these 6 critical seconds, the machine thought it was safe to fire, but hardware was still misaligned. Conflicting data led to lethal overdoses. Table in electron position, target not in place, magnets still in X-ray configuration, energy set to maximum. The software thought everything was ready. No mechanical interlocks existed to prevent firing. Result: massive overdose to the patient. Misleading error messages. The system displayed malfunction 54, meaning table not in correct position. Operators ignored it as minor errors were routine. This race condition, unsynchronized access to MEOS, was fatal, and no standard testing had detected it.
Therac-25 taught engineers hard lessons. Software must be thoroughly tested. Mechanical safety interlocks are critical. Operator interface must clearly communicate errors. Critical medical software cannot rely on a single developer or unverified assumptions. Modern radiation machines now combine software with mechanical fail-safes, preventing such disasters.
Therac-25 was designed to save lives, but instead it became a deadly cautionary tale. The tragedy reminds us that overconfidence in software can have real-world, fatal consequences. And the last unanswered question remains: who exactly wrote the code for Therac-25? AECL has kept that a secret. The one confirmed fact: the program was written by a single programmer in assembly language for the PDP-11 computer. If you found this story interesting, subscribe for more, and see you next time.